Hey guys, welcome to episode 2 of Data Every Day. Today we'll be looking at a dataset on Kaggle, Brazilian houses to rent. So if we take a quick look at it, we should see basically there are a number of features. It says 14. We're going to subtract the first two, so there's 12 features. And the city column is basically a binary classification column. We're going to use this as our label. Basically, we're going to use a number of features about a house to rent to predict whether or not it's in the city. So if it's in the city, it's 1. If it's not, it's 0. So very quickly we can notice it looks like we have a lot more positive examples than negative. Right? It says 5,249 examples for positive and only 831 for negative. So right away we realize we're going to have to make sure we take that into account. So let's go ahead and make a new notebook. Alright, and get started. So I'm going to start by importing Numpy and Pandas. And we're going to need, let's think about it. You know what, we can always import more later. Let's import these, and then we're just going to load in the CSV file. And I'll try to make this video quicker than yesterday's. Yesterday's dragged on for quite a while. So data is equal to pandas.readCSV and right there. Okay, and we can check data.print data.shape and get the head of the file of the dataset. Okay, so there we go. Alright, here's our 14 features. 12 features, I mean. And we can see right away that there's a duplicate index column. So we're going to want to drop that. And we have to do a significant amount of cleaning on this data, because you can see, first of all, we want numeric entries in our dataset. And here we have a lot of text entries, which we can easily convert into numeric entries because they're all binary. And over here, the prices have this $R sign at the front. So we're just going to have to strip that off it using regular expressions. Alright, so let's see. Okay. Let's start by dropping the index column. So we'll do data.drop. Column is, it has a weird name, so we'll use data.columns 0 to get the first column. The first axis, meaning column axis, and in place is true. So this should give us, if we check our here, let's make another. Let's just take these two lines and put it on its own block so we can run it multiple times. And we'll display the first 10. Alright, so now you can see we've dropped that column from our data. Next thing to do is start cleaning up these text entries. And you can see floor, if it doesn't have a floor entry, it's a dash. Let's just change that to a 0. So data dot Pandas has a great it's called replace function. So let's just take a look at that. Pandas replace. So you can see we specify a string to be replaced, a value to replace it with, and if we're using regular expressions or not. So in the case where we're replacing the full column name with another column name, we probably wouldn't need to use regular expressions. But in the since we're actually sorry, not column name, column entry is what I mean. In this case, since we have to strip this off the front and remove the comma, we're going to use regular expressions for that. But in this case, since we're just going to change the entire name, we probably won't have to. So let's go in and target each column specifically. So for the floor column, we're going to call replace on it, and to replace the dash with a 0. And this will use the numeric 0, even though it won't matter because we're going to cast it all to integers later. And then we also need regx. I'm not sure if we'll need this. Let's try it without. In place. It's true. Okay. So if we drop that, and we run this again, great. We can see that all those dashes have been converted into zeros, which is just what we need. Next, we're going to take animal and furniture and change the values to 0 and 1. So if it's not accept, we're going to make it 0, and if it's accept, we're going to make it 1. So straight up data animal dot replace. To replace value is not accept with 1c, value 0, in place true. And we'll do the same thing for the accept column, except the value is 1. Run this, check it out. Oh, it did not work. Oh, I didn't spell it right. There we go. Great. So not accept is now 0, and all the accepts are 1. Furniture. Okay. Same sort of idea. We can just copy this, change this to furniture, and replace not furnished and furnished with 0 and 1 respectively. So we run that, check out the dataset again. You can see now we have 0s and 1s in the furniture column. Okay, so things are looking good. We just have to take this off of the price columns. So what we can do is just do a for loop for each of those. So for column in, and we're going to get these names. Okay, just going to clean this up. Put the quotes on them. Okay. We will drop data dot data at column dot replace. To replace will be R, and since we have to use, since the $sign is a character used in regular expressions, we're going to have to put a backslash for it. Value, we'll just replace it with nothing. Now here we have to specify regx is true, and in place is true. And we can do the same thing for the commas. So replace commas with nothing. Okay, we run this. Oh, what's wrong here? Oh, I didn't put a comma here. Okay. Alright, let's take a look. And awesome, now we have numeric values. So the thing we can do to check to make sure that all of the numeric values, all of the values are numeric, is we can try to turn it into, we can try to cast the entire data frame into integers. So we'll set data is equal to data.asType, and we'll specify the type as numpy.int64. Oh, and we see we have an error, and it says there is something called seminfo somewhere in this. So to check that, we can, I'm pretty sure, yeah, we just write data.isIn, and then seminfo, and we want any column. So, aha, HOA column has seminfo. So all we need to do is check this. Okay. Somewhere in the HOA column there's an entry called seminfo. So what we'll do is just run another replace like this. Data HOA dot replace to replace seminfo value 0, right? This is a new, okay. Yeah, we'll just replace it with 0. That should be fine. And in place true. Check it out. If we check this again, fantastic. No longer is it an HOA. So now we can try casting it to int again, and we have another error, something called incluso. So we'll just check it in here. Incluso. And you can see 2 of our columns have incluso, HOA and property tax. So we'll go ahead and right here, HOA, just copy this, change this to incluso, copy the whole thing again. Now the other one was property tax, correct? Yes. Property tax. And great, we're going to change incluso to 0 also. So we run this, we can check. It has been removed, so we'll try turning it into integers, and it looks like it worked. So now the entire data frame has been turned into integer values. So normally I would do floats, but since it actually looks like, where's the actual, can I get the original data set? It looks like everything was already in integers. You see, before we started, there were no decimals, so it's fine to just turn it into ints. Alright, so now you can notice, okay, you know, before we do anything else, let's just do a quick shuffle of the data. So I like to do, so we do data, right, the sample function. Data.sample, fraction of the data is 100%, and we're going to reset the indexes and drop them afterwards. Okay, that should shuffle our data. It's been shuffled. You can see. Great. Okay. So next we will split the data between X and Y. So Y is just going to be our first column, as you can see above. City, right here, city. This is our label column, and all the others will be our feature column, feature columns, which will make up X. It's flickering. One sec. Okay. So Y will be data city. X will be data.drop city. That's simple. Run that. What's wrong here? Oh, that should not be. Sorry, that should not. This should be a parenthesis. Cities. Oh, we didn't specify the axis. Okay. So now if we take a look, X is everything except without city, and Y is just the label column, the city column, name city. So it looks like we have 6,080 training examples, and we can use Scikit-learn's train test split function to turn this into xtrain, xtest, ytrain, ytest. So from Scikit-learn.preprocessing, import train test split. Oh, sorry, it's not preprocessing. Model selection. Alright. So we can go ahead and split it by saying... Actually, before we split it, we can notice in the dataset, these values take on a large range of values in some of the columns, especially like here, right? 0, and then it goes up to 6,000. Here, as low as 145 to 0, all the way up to 3,000. It would make a lot of sense and be easier on the classifiers we choose to squish the data down, scale it between a value of 0 and 1. So there's Scikit-learn comes with a useful function for that. Actually, a series of them. I think there's multiple different scalars, but we're going to use the min-max scalar, which will just take the min and the max of the column and squish it down between 0 and 1. It'll still retain the relationships between the examples, but the actual scale of the values will be normalized. Okay, so we have min-max scalar. We're just going to make a scalar is min-max scalar, and scalar.fit our x, and then x is going to be scalar.transform x. So this is creating the object, fitting it to the data, finding the min-max basically, and then actually changing x to be the new values between 0 and 1. So if we run this, and then we can check x again, you can see it's a Numpy array, so we don't no longer need we're no longer get that nice beautiful view. So if we look at it as a data frame, we can just see, even though our column names are gone now, you can see all the values take on a value between 0 and 1. So that'll make it nice and easy on our classifier. Alright. So now we'll start processing the data to get it ready to put into the classifier. So xtrain, xtest, ytrain, ytest is equal to train test split. It's the Scikit-learn function. X, y. And the train size is going to be, let's do 80%. Okay. We'll run this. Check it out. Xtrain. We're going to get an array, but why don't we do .shape? Okay. So we have 4,864 examples and 12 features in the training set. And y should have the same number but with a single column. Yeah. Okay, and test. We have 1,216 examples. And y is the same. Great. So now we can start training our models because we have the data ready to go in. So I think we'll use 3 models. We can try it with logistic regression. We can try it with a support vector machine. And last we'll do a neural network. So we'll use everything from Scikit-learn today. So from Scikit-learn.linear model, I believe, import logistic regression from Scikit-learn.svm, import svc, support vector classifier, and from Scikit-learn.neural network, import Mlp Classifier, multi-layer perceptron classifier. Okay. So that's great. Alright, so let's start. So our model, we'll do the first model as logistic model is going to be logistic regression. And let's take a look at it. Scikit-learn logistic regression. We can see it takes a penalty or regularization function, and with the default solver, I think, what is the default solver? LBFGS. It says for LBFGS only supports L2 L2 regularization. So L2 seems fine. That's ridge regularization with trying to minimize the square values, squares of the weights. So let's do that. Let's do that. Okay, penalty is L2. What else we need? Okay. We'll leave the default solver, so we don't need to specify that. I'm pretty sure that's all we really need for logistic regression. Yeah, I'm trying to see, where's the regularization strength? It's not there. There's no lambda. Alright, well, it should be fine. I'll look into that. Let's go and just say verbose 1 so we can see what it's saying. And let's define our other models just now. SVM model. There's SVC. Let's take a look at that. Scikit-learn SVC. And so a support vector machine needs a kernel. We could choose probably either a linear kernel or a radial basis function kernel. I think we'll stick with the RBF just because it has good results. And C, our regularization parameter, we'll leave it at 1. It's this again, we're not really trying to optimize and optimize and optimize. We're just trying to get some data processing done and train it as quickly as possible. So let's go ahead and kernel is RBF, although I think that's the default value. And is there anything else we need? Don't think so. Don't think so. Okay, we'll just do verbose 1. And then our last one, NN model, is going to be Mlp Classifier. And we'll just look at that. Scikit-learn Mlp Classifier. Here. So hidden layer size we need to specify. And I think we'll leave the learning rate and batch size at the default. Shuffle is true by default. That's good. Okay. Alright. Let's do this. So, what do we need? What was the first thing? I already forgot. Hidden layer size. Hidden layer size. A tuple. 16 by 16 like we did in the last video. Just 2 hidden layers, each with 16 nodes. And then put that in the end. I'm just trying to see, is there anything else we need? Let's just specify the activation function. Even though the default is already ReLU, just do it so we can see what we're doing. ReLU activation function, and we'll do an optimization function. Solver is Atom. Okay, so these should be our models. Let's run them. And what did we do wrong? No comma. Hidden layer size. I got the name wrong. Hidden layer sizes. Sizes. Okay, so we got 3 models. We're going to fit them to the data, and then we're going to see how they perform. So let's fit each one. Log model dot fit x train y train. And we'll do the same thing for our SVM model, and the same thing for our neural network model. So, oh, nice. Okay, so they've all been fit. Cool. Now that they are fit, we will try something. We will check log model. Let's print log model.score, and we can try it on the test set by test. We'll do the same thing. For the other ones, SVM model and neural network model. Great. So these are some great accuracies. The problem is, if we look at data, let's go back to data. Okay, the first column. If we look at the number of unique values, no, actually, let's see. Okay, because it's just 0 and 1s, we can take the sum, right? The sum across to get the number of positive examples divided by the total number of examples. Let's see, how do we do that? Right, data.shape along the first dimension. You can see 86% of our data set is classified as a positive example. So this accuracy value, which is just the number of correct predictions over the total number of predictions, is not telling us very much. Because let's say we predicted positive. Let's say we predicted y equals 1 for every single example. Well, then 86% of the time we'd be right. You see? So the accuracy metric is only really good when you have equal number of positive and negative examples. So this is what we call skewed data, where the 0s and 1s are not in equal proportion. So we're going to use a different metric called the F-score, which basically, if you know what precision and recall is, F-score combines the two metrics in a way that gives you information about both of them. I believe. Okay, I'm not going to go into precision and recall, but I might make a video on that in the future. Right now, let's just go ahead and calculate this. I think Scikit-learn has an F-score. Scikit-learn.metrics import. It's also called F1 score. F1 score. All right. And then if we, okay, we're gonna have to make some predictions. So we'll say log predictions equals log model dot predict x test. We'll say SVM predictions equals SVM model dot predict x test. And neural network predictions equals neural network model dot predict x test. So these will be, okay. So now if you look at one of these, you see it'll just be an array, just like these are our predictions for the labels. And you see a lot of them are 1s simply because we have a lot more 1s than 0s. So to see how well our model did, we're going to call F1 score on the log predictions and the y-test. So it's going to compare them, calculate the precision, calculate the recall, and then calculate the F1 score to give us a better example of how we did. So I'm going to print that. Hold on. And we'll do the same thing for each model. And you can see our F score is actually quite good. 93, 93, 94. Looks like our logistic regression and support vector machine did very almost identical results. And our neural network performed slightly better. And the same thing is going on here. It's interesting to me that these are exactly the same number. If any of you know, if any of you guys know why that is, please let me know in the comments, because I have no idea what that's about. Alright, so I think that concludes today's video. Subscribe if you enjoyed watching, and make sure to like the video and leave any comments about things I can improve on, because I am very new to this, and I'm just I want to make these as clean and concise as possible. So thanks a lot. See you tomorrow.